Welcome back. Let's practice finding higher order partial derivatives. All right, so here's our first example. We want to find the second partial derivatives of this multivariable function. And we have a multivariable function of two independent variables, x and y. In this case, f of xy is equal to 7xy squared. Okay, so to find the second partial derivatives of a multivariable function, we have to start by finding the first partial derivatives. Because from each first partial derivative, we can find two second partial derivatives. All right, it works like this. We start with f of xy, and then we can take two partial derivatives, a partial derivative with respect to each of the independent variables. So what we can do is take a partial derivative with respect to x, which we can represent with f sub x, and then we can also take a partial derivative with respect to y, which we can represent with f sub y. And so those are the two first partial derivatives, but then for each of those, we can take another partial derivative with respect to each of the independent variables. So we can take a partial derivative with respect to x of fx and get fxx, and we can take a partial derivative with respect to y, which we could represent with f sub xy. In the same way, for fy, we can take a partial derivative with respect to y again, and that results in fyy, and you can also take a partial derivative with respect to x, resulting in f sub yx. All right, so these four partial derivatives right here are the second partial derivatives that we want to find for this multivariable function. So let's work on that. To begin, we do want to find fx and fy, the first partial derivatives. So let's find those first, beginning with fx. We want to take a partial derivative of this multivariable function with respect to x. And so that means that we will treat y as a constant. So for this function, 7x times y squared, this y squared would just be a constant. So you can think of it as any other number multiplied by 7x. And so for taking the derivative of this with respect to x, and x is to the first power, its derivative would just be its coefficient, or the constant being multiplied by x to the first power. And so that would just be 7y squared. All right, so the first partial derivative with respect to x would be 7y squared. But then what about the first partial derivative with respect to y, or fy? Well, now we're going to take a partial derivative with respect to y, so we will treat x as a constant. So that means that this 7x right here would just be the coefficient of y squared. Okay, so all we have to do is take a derivative of the y squared part, and that's it. So we would use the power rule for derivatives here, multiply that 2 down, subtract 1 from the exponent, and 2 times 7 is 14, so we get 14x times y to the first power. And so there we have it. Those are the first partial derivatives of this multivariable function, which we can now use to help us find the second partial derivatives. So let's start with finding these two, the second partial derivatives that we can find using fx. And so I'll start by finding fxx first, which would be the partial derivative with respect to x of the first partial derivative with respect to x. So we're going to take the partial derivative of 7y squared with respect to x. And there's no x's there, right? It's just 7y squared, and we're treating y as a constant, so this whole function would just be a constant whose derivative is 0. So fxx is equal to 0, but then what if we took a partial derivative of fx with respect to y? What would that second partial derivative be equal to? Well, we have 7y squared, but now we're not treating y as a constant. We're taking a derivative with respect to y, and so we would just use the power rule for derivatives here. Okay, so multiply that 2 down. 2 times 7 is 14. Subtract 1 from the exponent, and fxy is equal to 14y to the first power. All right, so those are two of our second partial derivatives for this function, but now there's two more left to find, and they are based on fy. We can take a partial derivative with respect to y and with respect to x of fy. And so let's start with fyy. Let's take a partial derivative of fy with respect to y. So we're going to treat x as a constant and differentiate with respect to y. And what we have here is 14xy, where we're going to treat that x as a constant. So 14x would be the coefficient of this y to the first power, and the derivative of y to the first power is just equal to its coefficient. So we get 14x as the second partial derivative where we differentiate with respect to y twice. All right, so that's fyy. And then finally, the last second partial derivative that we want to find is f sub yx, or in other words, the partial derivative with respect to x of fy. All right, so we're taking a derivative of this expression, but now with respect to x, not y. So we'll treat y as a constant, and x is now our variable. And so just like 14x was the coefficient of y to the first power, you can think of 14y as being the coefficient or the constant multiplied by x to the first power. And the derivative of x to the first power is just equal to its coefficient. So just think of it as that x disappearing, and then 14y is your derivative. All right, so the derivative of fy with respect to x is 14y. That is the last second partial derivative for this multivariable function. Okay, and so now we're done. We found all four of the second partial derivatives, but do notice for these two partial derivatives that involve both of the independent variables, we actually call these mixed partial derivatives. Notice that they are equal. They're both equal to 14y. That will always be the case. Whenever you are finding these second partial derivatives of a multivariable function, the mixed partial derivatives involving the same variables, in this case x and y one time, they will be equal. And you will see that throughout the rest of the examples in this video. All right, and so speaking of which, let's take a look at our next example. For this example, we want to find the second partial derivatives of this multivariable function, f of xy is equal to x cubed times y cubed minus 3x squared times y squared plus x to the power 4 plus y to the power 4 plus 8. Okay, so once again, just like with the previous example, there are going to be four second partial derivatives that we have to find. That will always be the case for a multivariable function of two independent variables. And so in order to find those, we do have to find the first partial derivatives first. So that's what I'm going to do here to start. Let's begin by finding the first partial derivative with respect to x, and I'm going to use a different notation this time around. Let's represent it with df dx. What would that be equal to? Well, we're going to take the partial derivative of this function with respect to x, treating y as a constant. So for this first term here, y cubed would just be a constant. So to take the derivative here, just use the power rule on x cubed, and you will keep y cubed as it is. So we get 3x squared times y cubed, and then moving on to the next term, once again, treat y as a constant, so this y squared would be a constant, just like 3. So just take the derivative of x squared, multiply that 2 down, and subtract 1 from the exponent. 2 times negative 3 is negative 6, so we get minus 6 times x to the first power times y squared. And then, moving on to the next term, we just have x to the power of 4. You can take the derivative of that using the power rule. You'll get 4x cubed. And then for the last two terms, y to the power of 4, that would be a constant because we're treating y as a constant, and 8 is also a constant. So the derivative of both of these terms is 0. The derivative of a constant value is 0. So we don't need to write anything else on the end there. All right, so that is df dx, or the first partial derivative with respect to x. But now let's find the first partial derivative with respect to y, df dy. And so let's go through all of that again, but now treating x as a constant and differentiating with respect to y. And so looking at the first term here, x cubed times y cubed, you would treat x cubed as a constant, so take the derivative of y cubed and leave x cubed alone. So multiply this 3 down and subtract 1 from that exponent, and you get 3x cubed times y squared. Then, moving on to the second term, we have negative 3x squared times y squared. Once again, treat x as a constant, so this x squared along with a negative 3 are just the coefficient of this y squared part. So take the derivative of y squared and leave the x squared part alone. So multiply that 2 down, subtract 1 from the exponent, and you'll get minus 6 times x squared times y to the first power. And then moving on to this term, x to the power of 4, there are no y's there, so this is entirely a constant with respect to y, right? We're treating x as a constant, so x to the power of 4 is still a constant, and its derivative with respect to y would be 0. So we don't need to worry about that term, but then y to the power of 4, we can use the power rule on, and you'll get plus 4y cubed And then finally, 8 is a constant, its derivative is 0. Okay, so now we have the two first partial derivatives of this multivariable function, and so now we can use them to find the four second partial derivatives. So let's start by finding the second partial derivative where we differentiate with respect to x twice. So that would be d squared f divided by dx squared. That's the notation when we take a partial derivative with respect to x of df dx. Okay, so look at this function here and treat y as a constant and differentiate with respect to x. So for this first term here, y cubed is a constant, but you can differentiate x squared, multiply 2 down, subtract 1 from the exponent, and you'll get 6x to the first power times y cubed. And then for the second term here, y squared would still be a constant, and so we're taking the derivative of x to the first power, which will just be equal to its coefficient, or the numbers multiplied by it. So that would be negative 6y squared. Just remove that x to the first power, and you have the derivative of that term. All right, so minus 6 times y squared. And then for the last term here, we have 4x cubed. You can find the derivative of that using the power rule. So we get plus 12x squared. And that right there is the second partial derivative, where you take a partial derivative with respect to x twice. Now let's find the partial derivative where we take the partial derivative of df dx with respect to y. And that notation looks like this. We have d squared f divided by dy dx. All right, the variable that you are taking a partial derivative with respect to comes first in the denominator of this expression. That's how this notation works. Okay, but to actually find this second partial derivative, we need to take the partial derivative with respect to y of df dx. And so starting with the first term here, remember, we are differentiating with respect to y, so y is the variable, and x we are treating as a constant. So 3x squared is just the coefficient of y cubed, so take the derivative of y cubed and leave x squared alone. Multiply that 3 down, subtract 1 from the exponent, and you'll get 9x squared times y squared. And then for the second term here, we're still taking a derivative with respect to y, so negative 6x is a constant, or the coefficient of that y squared, so leave it as it is and use the power rule on y squared. Multiply 2 down, subtract 1 from the exponent, and you'll get minus 12 times x times y. All right, and that would be it. The last term of 4x cubed is just a constant with respect to y, so its derivative is 0. And that right there is the second partial derivative, where you first take a partial with respect to x, and then a partial with respect to y. All right, so that's 2 of the second partial derivatives. Now let's find the other 2, which come from using df dy. Let's begin by just taking another partial derivative with respect to y. So that would be d squared f divided by dy squared. So we'll take a partial derivative of df dy with respect to y. So we're treating x as a constant. So looking at this first term, 3x cubed is a constant. It's the coefficient of y squared. So don't change anything here. Just take the derivative of y squared using the power rule. So we get 6x cubed times y. And then for the second term, again, we're treating x as a constant, so negative 6x squared is a constant, and differentiate y to the first power, whose derivative would just be its coefficient. All right, just get rid of that y, and you have the derivative of that term. You'll get minus 6x squared. Then for the last term, we have 4y cubed. There are no x's there, so this one should be pretty simple. Just use the power rule for derivatives, since we're differentiating with respect to y. So we have plus 12y squared. All right, so that's the second partial derivative, where we take a partial derivative with respect to y twice, which leaves us with just one more second partial derivative to find, which is the other mixed partial derivative. We already found one of them, but now let's find the other. They should be equal if we do it correctly. But the other one we have to find is when we take a partial derivative with respect to x of df dy. All right, so that looks like this. We'll have d squared f divided by dx dy. All right, and so let's take a partial derivative with respect to x of df dy. And so looking at the first term here, treat y squared as a constant and differentiate x cubed. Multiply that 3 down, subtract 1 from the exponent, and you'll get 9x squared times y squared. And then for the second term, this y would be a constant, so differentiate x squared, multiply that 2 down, 2 times -6 is -12, and subtract 1 from the exponent, and you'll have x to the first power. So we get minus 12 xy. And then finally, for that last term, there are no x's there, it's just 4y cubed, and we're treating y as a constant, so with respect to x, this entire term is a constant whose derivative is 0. So we don't have to write anything for that. We have found our last second partial derivative. This is the partial derivative where you differentiate with respect to y and then with respect to x. And do notice that it is exactly the same as this mixed partial derivative over here. It doesn't matter if you differentiate with respect to x first and then with y, or y and then x, you get the same second partial derivative. Next up, we want to find the second partial derivatives of this multivariable function. It is expressed in terms of the dependent variable. We have z is equal to e to the power of x times tangent of y. All right, so once again, just like with our previous examples, in order to find the second partial derivatives, we have to start by finding the first partial derivatives. And so I'll begin by finding the partial derivative with respect to x, and I'll represent that with this notation, dz dx. And so looking at our function here, we're going to treat y as a constant and differentiate with respect to x. So this tangent y is just a constant. You have tangent of some constant value, which would be equal to a constant value. So you could just think of this as a coefficient of e to the power of x, which is what we actually want to take the derivative of here, and the derivative of e to the power of x is just itself. So actually, nothing changes here. The partial derivative with respect to x of e to the power of x times tangent y is just itself. We get e to the power of x times tangent y back. Okay, so that was easy enough, but now let's find the partial derivative with respect to y, or dz dy. So now, e to the power of x will be treated as the constant because we're treating x as a constant. So we just have some number or some coefficient in front of tangent y, which is what we actually want to take the derivative of since it's in terms of y. And remember that the derivative of tangent is secant squared. So for dz dy, we keep that e to the power of x, and then the derivative of tangent y is secant squared y. All right, so that would be the partial derivative with respect to y. So now we have the first partial derivatives. Now let's use them to find the second partial derivatives, starting with the second partial derivative where we differentiate dz dx with respect to x. So that would be d squared z divided by dx squared. What would that be equal to? Well, it's essentially the same thing we've done before, because when we took a partial derivative with respect to x of z, we got the same function back. So if we're taking a partial derivative with respect to x again, we're going to get the same function again, right? We're treating tangent y as a constant, and the derivative of e to the power of x is itself, so we still just get e to the power of x times tangent y. All right, so that's one of our second partial derivatives. But now let's find another, specifically when we differentiate dz dx with respect to y. So that would be d squared z divided by dy dx. What would that be equal to? Well, it's actually going to be the same as dz dy, because dz dx, the function that we're actually going to take the derivative of with respect to y, is the same as the original function. Okay, we're treating e to the power of x as a constant and only need to differentiate tangent y because it's in terms of y, and the derivative of tangent y is secant squared y. Okay, so d squared z divided by dy dx is just e to the power of x times secant squared y. That is the second partial derivative, where you first take a derivative with respect to x and then with respect to y. Okay, now moving on to dz dy, we need to take a partial derivative with respect to x and with respect to y of that function to get the other two second partial derivatives. So let's start by taking another partial derivative with respect to y. So that would be d squared z divided by dy squared. So if we take the derivative of e to the power of x times secant squared y with respect to y, we only have to take the derivative of secant squared y, right? E to the power of x would just be a constant because we're treating x as a constant. And so we just have to focus on secant squared y, which does seem a little tricky at first, but remember that that is the same as secant y squared. So really what we have here is a composite function that we can take the derivative of using the chain rule. The outside function is the quantity squared, and the inside function is secant. So we'll start by taking the derivative of the outside function, use the power rule, keep that same inside function, and then multiply by the derivative of the inside function. All right, so here's what we get. Keep that e to the power of x on the outside, then multiply by the derivative of secant squared y. So the 2 comes down, you have 2 times secant y, and it is just secant y because you subtract 1 from the exponent and you have secant to the first power. But then you need to multiply by the derivative of secant y. And the derivative of secant is secant times tangent. So we get times secant y times tangent y. All right, so simplifying here, I'm going to pull this 2 out front. So we have 2 times e to the power of x, and then we have 2 secant y's that can be multiplied together, giving us secant squared y, and then don't forget about that tangent y on the end. So we're multiplying by tangent y. And that right there is another second partial derivative, specifically where we are taking a partial derivative with respect to y twice, which leaves us with just one more second partial derivative to find, which is when we take a partial derivative with respect to x of dz dy. And so that would look like this, d squared z divided by dx dy. All right, so what would that be equal to? Well, we're differentiating dz dy with respect to x, so we're treating y as a constant. So secant squared y is just a constant value, right? You'd have secant squared of some constant value, which would still be a constant. So the only thing we have to take the derivative of here is e to the power of x, and the derivative of e to the power of x is just itself. So actually, nothing changes here. We just get e to the power of x times secant squared of y, and that is that second partial derivative. Which makes sense, because both of our mixed partial derivatives here are the same, as they should be. It doesn't matter if we differentiate with respect to x and then y, or if we start with y and then x. We get the same function, or the same partial derivative, of e to the power of x times secant squared y. For our next example, we want to find the second partial derivatives of this multivariable function. Z is equal to the natural log of x minus y. Okay, so let's start by finding the first partial derivatives. We have to have those before we can find the second partial derivatives. So let's begin by taking a partial derivative with respect to x. I'm going to use a different notation this time. Let's use this notation, zx. And so if we're taking a derivative with respect to x, we're going to treat y as a constant. And so what do we do here? Well, we have an x inside of the natural log function, so we do have to take the derivative of that natural log function. And remember that the derivative of a natural log function, which in part does use the chain rule, is 1 divided by that inside function multiplied by the derivative of that inside function. So what we get for zx is 1 divided by x minus y times the derivative of x minus y. But what would the derivative of that be? Well, the derivative of x is 1, and the derivative of negative y would be 0 because we're treating y as a constant. So the derivative there is 1 minus 0, which would just be 1. So we're multiplying 1 divided by x minus y by 1, which doesn't change anything. So the partial derivative of z with respect to x is just 1 divided by x minus y. All right, so that's good. That is zx. But now let's find zy, or the partial derivative with respect to y. And so once again, y is inside the natural log function, so we do have to take the derivative of the natural log function, which will be 1 divided by that inside function, multiplied by the derivative of that inside function, but this time with respect to y. Okay, remember that. We're treating x as the constant now. So the first part is the same. We still have 1 divided by x minus y, but now we're multiplying by the derivative of x minus y with respect to y. So the derivative of x would be 0, because x is a constant with respect to y, and the derivative of negative y would be negative 1. So we're multiplying by negative 1, which you could simplify by just multiplying negative 1 into the numerator, and you'd have negative 1 divided by x minus y. Okay, and so with that, we have the first partial derivatives of this multivariable function. So now let's use them to find the second partial derivatives. And so let's first find zxx, or the partial derivative of zx with respect to x. All right, so we have to take the derivative of 1 divided by x minus y with respect to x, treating y as a constant. And so you have a couple options here. You could try to use the quotient rule, but I think an easier way to go about this, since x is not in the numerator and denominator, it's only in the denominator, what you could do is move this quantity to the numerator by making the exponent negative, and then you avoid using the quotient rule and just have to use the chain rule. Okay, so another way to write this would be x minus y to the power of -1. And so that's a little bit easier to take the derivative of in my mind. We can just use the power rule on the outside function and then multiply by the derivative of the inside function. But as we pointed out earlier, the derivative of x minus y with respect to x will just be 1. The derivative of x is 1, and the derivative of -y is 0 because we're treating y as a constant. All right, so what we get here for zxx is negative x minus y to the power of -2. Don't forget to subtract 1 from that exponent, and then technically you're multiplying by 1, but that doesn't change anything, so you don't have to write that if you don't want to. But then rewriting this, moving this quantity to the denominator so that the power is positive, zxx is -1 divided by x minus y squared. All right, so that is one of our second partial derivatives, that is zxx. Now let's find the second partial derivative where we differentiate zx with respect to y. So that would be z sub xy. What would that be equal to? Well, it's very similar to the derivative that we just found. Even though we're going to be differentiating with respect to y now and treating x as a constant, we still have to use the same method. Y is in the denominator, so either we have to use the quotient rule here, or we can rewrite the function like this so that we can use the chain rule. Okay, if there's a function of y in the numerator and denominator, you would probably want to keep it this way and just use the quotient rule. But since it's just a constant of 1 in the numerator, rewriting the function in this way to then take a derivative is much easier in my opinion. So taking the derivative of this with respect to y, we're still going to use the power rule on the outside function, but then we're multiplying by a different derivative because now we're multiplying by the derivative of the inside function with respect to y, which will not just be 1, but -1, right? X would just be a constant, so its derivative is 0, but then -y, the derivative of that would be -1, so you're multiplying by -1. Okay, so you multiply the -1 down, you get negative x minus y to the power of -2 because you subtract 1 from the exponent, and then we're multiplying by the derivative of the inside function, which is -1. Okay, and so simplifying, those two negatives would cancel out, and you can move this quantity to the denominator to make that power positive, leaving you with 1 divided by x minus y squared. That is the second partial derivative, zxy. Okay, now that's only 2 of our second partial derivatives. We still have 2 more to find, and we can find those using zy. Let's start by taking another partial derivative with respect to y, so that would be zyy. We'll take a partial derivative with respect to y of this function zy. And so how would we take the derivative of this with respect to y? Well, it's pretty much the same thing we did before when we were working with zx. The only difference here is that the numerator is negative. So I would recommend that you once again rewrite this function. It would be negative x minus y to the power of -1, and so then you could use the chain rule to take the derivative with respect to y of this function. Multiply that -1 down, subtract 1 from the exponent, and then multiply by the derivative of the inside function, which with respect to y, as we've done multiple times now, the derivative of x minus y will be -1, because we're treating x as a constant, and the derivative of -y is -1. All right, so we have negative, and then we're multiplying the -1 down, times x minus y to the power of -2, and then we're multiplying by another -1. That's the derivative of the inside function with respect to y. Okay, now these two negatives will cancel out, but we still have this -1 over here. So our final answer will be negative. What we will get is -1 divided by x minus y squared. Okay, I move this quantity to the denominator, giving it a positive exponent. And so that right there is zyy. And so then we just have one more second partial derivative to find, which would be z sub yx, where we take a partial derivative with respect to x of zy. All right, and once again, it's a very similar process. Since x is just in the denominator, not in the numerator, it is helpful to rewrite the function in this way so that you can then use a chain rule. It's just that in this case, the derivative of the inside function will just be 1, because with respect to x, the derivative of x is 1, and the derivative of negative y is 0. All right, so here's what we get. Multiply that negative 1 down, and you'll have negative 1 times x minus y to the power of negative 2, because we subtract 1 from that exponent, and then you'd be multiplying by 1. That's the derivative of the inside function, but that doesn't change anything, so I'm not going to bother to write that. But simplifying, these two negatives cancel out, and then you can move this quantity to the denominator, giving you a final answer of 1, that is positive 1, divided by x minus y squared. And that right there is the second partial derivative, zyx. Okay, and just as I pointed out earlier, these two mixed partial derivatives that involve taking partial derivatives with respect to both x and y are equal. And in this case, the other two second partial derivatives are equal as well. That doesn't always happen, but in this case it did. Both zxx and zyy are equal to the same expression, which is pretty neat. Hey, real quick, before we take a look at the next example, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. Next up, we want to find the second partial derivatives of this multivariable function. We have f of xy is equal to arctangent of y divided by x. And arctangent, of course, is the inverse tangent function. So you could also read this as inverse tangent of y divided by x. Okay, so the first thing we want to do here is find the first partial derivatives. That way we can use those to find the second partial derivatives. And so I'll start by finding the partial derivative with respect to x, or fx. And so how do we take the derivative of arctangent of y divided by x, particularly with respect to x? All right, we will treat y as a constant, but both x and y are inside the arctangent function, so we will have to take the derivative of the arctangent function. It doesn't matter if we're differentiating with respect to x or y, that will always be the case. And so remember, this is a derivative rule from Calculus 1. The derivative of arctangent is 1 divided by 1 plus the inside function squared multiplied by the derivative of the inside function. All right, more generally, d du of arctangent of u is equal to 1 divided by 1 plus u squared times u prime. All right, it's 1 divided by 1 plus the inside function squared times the derivative of that inside function. So in this case, the inside function is y divided by x. So we would get 1 divided by 1 plus y divided by x squared times the derivative of y divided by x with respect to x. And so that's a little bit tricky because x is in the denominator, but we could rewrite it so that's a little bit easier to work with. Remember that y divided by x would be the same as y times x to the power of negative 1. You can move x to the numerator by making its power negative, and then we're just treating y as a constant, so you can take the derivative here by using the power rule for derivatives. Just multiply that negative 1 down and subtract 1 from the exponent. So the derivative here would be negative y times x to the power of negative 2. All right, so then simplifying, this will be equal to 1 divided by 1 plus y divided by x squared. I am going to square each part, so we have y squared divided by x squared, and then we're multiplying by negative y divided by x squared. Okay, I just moved that x to the power of negative 2 to the denominator, making the power positive. And now we can simplify by multiplying negative y into the numerator, and then x squared into the denominator. You'd multiply it by 1, and by y squared divided by x squared, where the x squareds would cancel out. So what we get here is negative y divided by x squared plus y squared. Okay, so sort of a tricky derivative, but we were able to find it. That's just fx, the first partial derivative with respect to x. Let's also find the first partial derivative with respect to y. So that would be fy, and that will be equal to a very similar derivative. We're still taking the derivative of arctangent of y divided by x, but now with respect to y. And we still have to use this derivative rule because y is also inside of the arctangent function. So once again, we will have 1 divided by 1 plus y divided by x squared, but now we're multiplying by the derivative of that inside function with respect to y. And that's going to be a little bit easier this time around because y is in the numerator. So that means that 1 divided by x would just be its coefficient. It's as if you had y divided by 2 or y divided by 3. The derivative of that would just be the coefficient of 1/2 or 1/3. So in this case, it would be 1 divided by x. Okay, so we're multiplying by the derivative of that inside function, which will just be 1 divided by x. So then simplifying, this will be equal to 1 divided by 1 plus y squared divided by x squared. I do want to square both of those parts. That way we can simplify this as much as possible, but then we're still multiplying by 1 divided by x. And we can multiply x into the denominator, multiply it by 1, and by y squared divided by x squared, it will cancel out with one of those x's. So what we get is 1 divided by x plus y squared divided by x. But to make that a little bit nicer, what we can do here is multiply by a form of 1 of x divided by x. Right, you can do this because anything divided by itself is 1, and multiplying anything by 1 doesn't change its value. Anything times 1 is itself. So this is a legal move, but by doing this, this x will be multiplied by this x, and we get x squared, and then x times this quantity, these two x's just cancel out, leaving you with y squared, which I think is much easier to work with. Okay, you will be left with an x in the numerator, but I think that's a nice trade-off rather than having a fraction within a fraction. So, rewriting this, I'm just going to add on that form of 1 right here, and then we'll rewrite the function as x divided by x squared plus y squared. And that right there would be fy, the first partial derivative with respect to y of this function. Okay, so now we do have our first partial derivatives for this function. Now let's use them to find the second partial derivatives. And let's start by taking a partial derivative with respect to x of fx. So that would be this second partial derivative, fxx. And so if we take a partial derivative with respect to x of fx, what would that look like? Do we need to use the quotient rule here? Well, no. Even though we have a fraction, you want to be looking at where the x's are, the variable that we are taking a derivative with respect to, and it's only in the denominator, so you don't have to worry about the quotient rule here. What I would do is move this quantity to the numerator, make the power negative, and then you can use the chain rule, since you'd just be treating negative y as a constant, right? We're differentiating with respect to x, so all the y's will be treated as constants. So rewrite the function like this. You'll have negative y times x squared plus y squared to the power of negative 1. And now you can use the chain rule, take the derivative of the outside function, which is this quantity to the power of negative 1. You'd multiply that negative 1 down and then subtract 1 from the exponent, and then you'd have to multiply by the derivative of the inside function, specifically with respect to x. Okay, now let's do one piece of that at a time. Let's multiply that negative 1 down first. Negative 1 times negative y will be positive y. So we get y times x squared plus y squared to the power of negative 2. We subtracted 1 from that exponent. Then let's multiply by the derivative of that inside function with respect to x, which would just be 2x, right? X squared, the derivative of that is 2x, and then y squared, that is a constant with respect to x, so the derivative is 0. Okay, so we multiply by 2x. And so simplifying, 2x and y will stay in the numerator, and then we'll move this quantity back to the denominator so the power is positive. So this would be equal to 2xy divided by x squared plus y squared squared. All right, there's a lot of squareds going on there, so don't miss any of them. You need one for x, y, and that quantity. And that right there is a second partial derivative. Specifically, it's fxx. We still have 3 more to find here, and so let's work on the next one. Let's take a partial derivative with respect to y of fx. That will be f sub xy. And so what would that be equal to? Well, we're going to take a derivative of fx, but with respect to y. And so now we do have to use the quotient rule because y is in the numerator and the denominator. All right, we have a function that includes y divided by another function that includes y. So we do want to use the quotient rule here. All right, so let's set it up. In the numerator, we'll start by taking the bottom function, which is x squared plus y squared, and multiplying it by the derivative of the top with respect to y, right? Remember, we are taking a partial of fx with respect to y, and the derivative of negative y with respect to y is negative 1. So we multiply by negative 1, then we will subtract that top function, which is negative y, multiplied by the derivative of the bottom with respect to y. And so x squared would be a constant, so that the derivative of x squared would be 0. The derivative of all constants is 0. But then for y squared, that derivative would be 2y using the power rule. So we're just multiplying by 2y. All right, and then in the denominator, we just rewrite the bottom function, but square it. So we have x squared plus y squared squared. Now simplifying, we want to multiply negative 1 by both of these two terms. So in the numerator, we have negative x squared minus y squared. These two negatives will cancel out, so you have positive y times 2y, giving you plus 2y squared, and then you still have that denominator of x squared plus y squared squared. But we're not done yet. We have some like terms in the numerator. Negative y squared and 2y squared can be combined to be positive 1y squared. And so I would rewrite that like this. We'll have y squared minus x squared divided by x squared plus y squared squared. Okay? And that right there is fxy, the second partial derivative where we take the partial derivative with respect to y of fx. And so now we found 2 of the 4 second partial derivatives that we want to find. And so now let's work on the last 2, which are going to come from differentiating fy. So let's start by taking a partial derivative with respect to y of fy. That will give us this second partial derivative, fyy. That will be equal to the derivative of fy with respect to y, and there is only a y in the denominator, okay? We're treating these x's as constants, so we don't have to use the quotient rule here. Since y is only in the denominator, that being the variable we're differentiating with respect to, we can make our lives a little bit easier by moving that denominator to the numerator by making the exponent negative and then using the chain rule. So rewriting this function, we'll have x times x squared plus y squared to the power of negative 1. All right, that's going to be a little bit easier to work with when we're taking a derivative with respect to y. When we come back in just a bit and differentiate fy with respect to x, we will have to use the quotient rule then because x is in the numerator and denominator. But let's not get ahead of ourselves. Let's just work on fyy for right now. Let's differentiate this function with respect to y. You're going to use the chain rule, starting with the derivative of the outside function for this composite function. So multiply that negative 1 down, subtract 1 from the exponent, and multiply by the derivative of the inside function with respect to y. So multiplying the negative 1 down, you'll get negative x times x squared plus y squared to the power of negative 2. And then you want to multiply by the derivative of the inside function, which with respect to y will be 2y, right? The derivative of x squared would be 0 because we're treating x as a constant, so x squared is a constant whose derivative is 0. And then y squared using the power rule, that derivative is 2y. So we're multiplying by 2y. Okay, and then simplifying, in the numerator, we'll have negative 2xy, right? We have the 2 here. This negative will make it negative 2. And then we have an x and a y, and then moving this quantity to the denominator by making that power positive, we have x squared plus y squared squared. And that right there is the second partial derivative, fyy, for our multivariable function. It's what we get after taking a partial derivative with respect to y 2 times. And so that just leaves us with one more second partial derivative to find, which is when we take a partial derivative with respect to x of fy. So that would be f sub y x. Okay, so at the end, we should get the same thing that we got for f sub xy, but I'm not just going to rewrite the function. I do want to show you where it comes from. So let's take a partial derivative with respect to x of fy. As I mentioned earlier, because we are now differentiating with respect to x, and x is in both the numerator and the denominator, we have a quotient of functions in terms of x, so we will have to use the quotient rule. So let's set that up. In the numerator, we'll start by taking the bottom function, which is x squared plus y squared, multiplied by the derivative of the top, and the derivative of x would just be 1. So that's easy enough. We're just multiplying by 1, but really you don't even need to write that. So I'm just going to write x squared plus y squared, just like that, and then we'll subtract the top function, which is x, times the derivative of the bottom with respect to x. And the derivative of x squared is 2x, and then the derivative of y squared would be 0, right? Y squared would be a constant. Since we are differentiating with respect to x, we are treating y as a constant, so the derivative of that constant would be 0. So altogether, the derivative of that bottom function would just be 2x, and so we'll multiply that by x. And then in the denominator, we will have the bottom function squared. So x squared plus y squared squared. Okay, now simplifying, in the numerator here, x times 2x, that would just be 2x squared. I'm just going to rewrite that right here. We have 2x squared, and then we have some like terms that we can combine. X squared and negative 2x squared would combine to be negative x squared. So what we get here is y squared minus x squared divided by x squared plus y squared squared. All right, that is the second partial derivative, fyx, for this multivariable function. And so now we have found all 4 second partial derivatives. And the mixed partial derivatives here, fxy and fyx, are the same, so we know that we did both of those derivatives correctly. Let's take a look at one more example for this video. For our last example, we want to find f sub xxx, f sub yyy, f sub zzz, and f sub xyz for this multivariable function, which is a multivariable function of 3 independent variables. We are given f of xyz is equal to x squared times y times sine z plus y cubed times z times cosine x. All right, so this time around, we're not just finding second partial derivatives, we are actually finding third partial derivatives. Not all of them, there would be way more than what is listed here. We just want to find these 4 in particular. This first one being the partial derivative with respect to x 3 times, then the partial derivative with respect to y 3 times, and then the partial derivative with respect to z 3 times, and then this last one, we take a partial derivative with respect to each of the independent variables. We start with x, then y, then z. But for all 4 of those, we are taking a partial derivative 3 times, indicated by the 3 letters in the subscript, so we know that they are a third partial derivative. Okay, so let's start with fxxx. To find that, we first have to take the partial derivative of this function with respect to x, then we'll have to do it again, and then again. So let's find fx. We want to take a partial derivative of this function with respect to x, meaning that we will treat the other independent variables as constants, that being y and z. So looking at this first term here, this x squared is the only part that we want to take the derivative of. This y would be a constant, and sine of z would also be a constant. We're treating z as a constant, so sine of a constant value would still be constant. So just take the derivative of x squared using the power rule and leave everything else alone in that term. You'll multiply the 2 down, subtract 1 from the exponent, and you'll get 2x to the first power times y times sine z. Okay, then for the second term, y cubed would be a constant, z would be a constant, but cosine x is in terms of the variable that we are taking a derivative with respect to. So we do need to differentiate cosine x, and the derivative of cosine is negative sine. So keep everything else the same. Y cubed and z are just the coefficient of cosine. So our derivative here will be negative y cubed times z times sine x. Okay, I just put that negative out front rather than keeping it with the sign. And so that would be fx. That's the first partial derivative with respect to x. But now let's take the partial derivative with respect to x again. So that would be fxx. We have to find this first before we can find fxxx. And so let's work on that. We need to take a derivative with respect to x again, but now of fx. So looking at this first term here, x is to the first power, so the derivative of that term will be everything else but x. Okay, just take that x out and you have the derivative because everything else here is a constant. We're still treating y and z as constants, so we just get 2y times sine z. Okay, and then for the second term here, once again, y cubed and z are still constants with respect to x, so we just have to take the derivative of sine x, and the derivative of sine is cosine. So we get minus y cubed times z times cosine x. All right, so that is fxx, but now let's take a partial derivative with respect to x one more time, and we'll get fxxx, which will be equal to the derivative of these two terms, but with respect to x. And so for this first term, there's no x's there, so with respect to x, that is just a constant. Its derivative is 0. So don't worry about that term. Let's move on to the next one here. We have negative y cubed z times cosine x. Cosine x is the only part we have to worry about. It's the only thing in terms of x, and the derivative of cosine is negative sine, so that negative will cancel out with this negative, just leaving you with positive y cubed times z times sine x. All right, and that right there is fxxx. It is the third partial derivative of this multivariable function where we differentiate with respect to x 3 times. So now let's move on to fyy. We're going to do the same thing, but take a partial derivative with respect to y each time. So we have to begin by finding fy, the first partial derivative with respect to y of this function. So looking at the first term here, we have y to the first power, and everything else is in terms of the other independent variables. So those parts are just constants. Just take the derivative of y to the first power, which would be equal to its coefficient, or any constants multiplied by it. So really, just take out that y, and you get the derivative of that first term with respect to y. You'll get x squared times sine z. And then for the second term here, we have y cubed times z times cosine x. Z and cosine x are just constants with respect to y, so take the derivative of y cubed using the power rule and leave everything else alone, so you'll get plus 3y squared times z cosine x. All right, so that's fy, but then let's take a partial derivative with respect to y again. That would be fyy, and so we're taking a partial derivative of fy with respect to y. And looking at the first term here, there are no y's there. Everything is in terms of x and z, which with respect to y are constants. So this whole term is a constant whose derivative is 0. So let's just move on to the next term here, where we have 3y squared z cosine x. And so again, z and cosine x are just constants. So just focus on the y squared part, use the power rule, multiply that 2 down, subtract 1 from the exponent, and you get 6y to the first power times z cosine x. All right, and then finally, let's find fyy by taking another partial derivative with respect to y, but this time of fyy. If we do that here, there's only one term to work with, and there's only one y within it. It's this y right here to the first power, so its derivative will be all the constants multiplied by it. Everything else here is just a constant, 6z cosine x, all constants with respect to y, so the derivative of y to the first power will just be those constants, 6z times cosine x. All right, that right there is fyy. And so now let's move on to fzzz. We're going to do the same thing again, but take the derivative with respect to z 3 times. And so we have to start by finding f sub z. which is the first partial derivative with respect to z of this function. So looking at the first term here, x squared and y are just constants with respect to z, but we do need to take the derivative of sine z since it's in terms of z, and the derivative of sine is cosine. So keep the constants out front and differentiate sine, giving you x squared times y times cosine z, and then the derivative of the second term, y cubed times z cosine x. Y cubed and cosine x are constants with respect to z, and the derivative of z to the first power would just be its coefficient. So just remove that z, and you get the derivative of that term. We'll have plus y cubed times cosine x. All right, so that's the first partial derivative with respect to z of this function. Now let's take another partial derivative with respect to z, so that would be f zz. Looking at the first term here, x squared times y is still a constant. It would be the coefficient of cosine z. So just take a derivative of cosine, which will be negative sine, giving you negative x squared y times sine z. And then for the second term here, there are no z's. So this whole term is a constant. We are treating x and y as constants when we differentiate with respect to z. So this term is a constant whose derivative is 0. So you could add 0 on the end there, but that's not necessary. This is the derivative with respect to z of fz. So now we can find fzzz by taking another partial derivative with respect to z of this function, fzz. And negative x squared times y is still a constant with respect to z, and so the only part we have to take a derivative of is sine of z. And the derivative of sine is cosine, so our result here is negative x squared times y times cosine z. That is the third partial derivative where we take a partial derivative with respect to z 3 times, fzzz. Okay? And so that leaves us with just one more higher order partial derivative to find, and that is f sub xyz. In order to find that, we first have to find fx, and then take a partial derivative of that with respect to y, and then take a partial derivative of that with respect to z. Okay, the order of the letters here tells you the order in which to do the partial derivatives, and so we already have fx, that's right here, we found that earlier, so we can find fxy by taking a partial derivative with respect to y of that function. So let's do that here. F sub xy will be equal to the derivative with respect to y of these two terms. Looking at the first one here, y is to the first power, so the derivative of that will be its coefficient, which is everything else here. 2x and sine z are just constants with respect to y, so just remove that y and you have the derivative with respect to y. So we get 2x times sine z, and then for the second term, y cubed is in terms of y, but everything else is in terms of the other independent variables, so those are just constants. You can take the derivative of y cubed and be done. So use the power rule, and you'll get minus 3y squared times z times sine x. All right, and so that is f sub xy. Now, we're almost done. We can find f sub xyz by taking a partial derivative of fxy with respect to z. All right, so fxyz will be equal to the partial derivative of fxy with respect to z. So looking at the first term here, 2x would be a constant, but we do need to differentiate sine z. The derivative of sine is cosine, so we get 2x times cosine z. And then for the second term here, we have z to the first power, and everything else would be a constant. Everything else is in terms of the other independent variables, which we're treating as constants. So the derivative of z to the first power would just be those constants. So remove that z, and you have the derivative. Minus 3y squared times sine x. All right, and that's it. That is the third partial derivative, where we take a partial with respect to x, then y, and then z. And so we have completed this example. Okay, and so with that, this was the last example for this video, but if you do want to get some more practice working with higher order partial derivatives, I do have more on my membership site. So if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.